Okay, this is the video walkthrough of example 6.2.1 in the chapter 6 notes. So section 6.2, we get into transformations with variables, with random variables. What happens to means and standard deviations of a variable such as x if we multiply every value of the variable by a constant, or perhaps if we add or subtract a constant from every value of a variable. And eventually, we will also look at what if we add variables to each other. If I have a variable x plus y, for example. All right, so in this example, we have privileged Preston. His parents are worried about grades. Maybe he's not the most studious student. Let's suppose the variable x represents the number of A grades that Preston earns in a semester. And this will be a discrete quantitative variable. The number of A's that are earned has to be a whole number. For Preston, let's assume he can't earn more than 3 A's. So it's either 0, 1, 2, or 3 A's. And we see the probabilities associated with each of those as well. Okay. Feel free to use our formulas from 6.1 to double check the mean of x and the standard deviation of x. It's good practice to do that. But I am giving those results here. We're not going to do the calculation in this example right now. Part A, Preston's parents will incentivize him by giving $500 for every A earned. I wish Preston's parents were mine, but they are not. Let's define a new variable to represent not the number of A's, but rather the amount of money that Preston is going to earn. So I'm going to give it a name, M. M equals money earned. I'm going to define that right away. And the calculation for M is really just a transformation of the previous variable x. I can take the x value, which is number of A's, and simply multiply any of those values by 500 to get the money earned. So I'm going to say M equals 500x. Okay. How does this affect mean standard deviation? The mean is quite intuitive. If I'm multiplying every value of a variable by a constant, measures of center and location also get multiplied by that constant. In other words, I can take the original mean of x, which was 1.1, and simply multiply that by 500, and I get 550. This is the mean amount of money that Preston's going to earn in a randomly chosen semester. Similar for standard deviation. As long as I'm multiplying by a positive number, I can simply multiply a previous standard deviation upon a transformation. So if the original standard deviation was 0.943, the standard deviation for amount of money earned, standard deviation of M, is 500 times 0.943. Notice that both of these results are in the units of dollars. Okay. Part B, this time we want to measure a profit. It appears that Preston is paying studious Stan to do all of his homework for $75. So Preston's going to be making some money off of his parents, but he's giving some of it up to Stan. Our new variable T for total profit would be the amount of money earned in a semester minus the 75 that he's paying Stan. Okay, so how does an addition, or in this case, subtraction, affect means and deviations? Well, for means, we're going to apply the same transformation. If I'm subtracting 75 every time we earn the money, if I'm always subtracting 75, the mean itself will be reduced by 75. So mu of t equals the mean amount of money earned, which we calculated above, minus 75, $475. We have to be careful with standard deviation because transformations with addition or subtraction of a constant do not affect overall spread of a distribution. If I shift all the possible money amounts by 75 uniformly, those amounts are still the same distance from each other. They're not further apart or closer together. The spread has not changed. We've just shifted everything down the number line. So we have to recognize with this transformation not to modify the standard deviation at all. Standard deviation of t is the same as it was for m, so $471.50. Let's check out part C, where now we've got oblivious Oliver, who's got a similar deal with the parents, but is getting paid a lesser rate for A's. Okay. The variable y will be the number of A's earned by Oliver. And it appears, according to the table, that Oliver is not capable of earning more than 2 A's. It's either 0 or 1 or 2 appears to even be a stretch. Okay. So now let's consider the total number of A's earned by Preston and Oliver combined. I'm going to give it a name of n. Really, I could just keep calling it x plus y because that's what it is. It's an x value, which represents the number of A's that Preston earns, plus a y, which is a separate variable representing number of A's earned by Oliver. So n equals x plus y. Okay, what happens to the mean? Mean is, as always, fairly intuitive. The mean of n, or the mean of x plus y, is just the mean of x plus the mean of y. Okay, both of those means were given earlier in the prompt, so I'm just adding them together to get the mean number of A's. As usual, the standard deviation story is a bit more complicated. In fact, we are not allowed to add standard deviations from variables together. At least if we do, we shouldn't expect to get a correct answer. Okay, I'm not going to get into the theory of that in this video, but we're not allowed to do it. We are, however, allowed to add variances. Okay, if I want to find the new variance for this sum of two variables, I can take the standard deviations that we already had, I can square them each to make a variance, and I can add those together. But most likely, when I do that, I'm still going to be interested in the standard deviation. So once I have this summation for a new variance, I do have to then take a square root to turn it back into a standard deviation. All right, so this formula is perhaps not what we would have expected, but it is the one that is correct. What it honestly reminds me of is Pythagorean theorem in a way. It's going to feel like you're doing a Pythagorean theorem problem to figure out a new standard deviation. Okay, if you treat the original deviations each as like the leg of a triangle, the hypotenuse that we would solve for is the new standard deviation. So that's what I'm doing here. Taking both of the deviations from above, I'm squaring them, I'm adding them, I'm taking a square root. Okay. As we move down the page, this will get a little more complicated. In part D, we see two types of transformations together. I see the adding of two variables, but also multiplying each of those variables by a constant. So here we want to find the total amount of money paid out by the parents, which really they're paying 500 for every A from Preston and then 300 for every A from Oliver. Hence, Z, if we want to give it a new name, is equal to 500x plus 300y. The mean of Z is still intuitive. I'm going to take 500 times the mean of x plus 300 times the mean of y. I'm basically swapping the means in where I see an x and a y in the definition of Z, and I can expect that to work. Looks like the mean amount of money paid out is $760. Standard deviation, we have to be more careful. Because we're adding two variable quantities, we're going to see this Pythagorean theorem adjacent trick again, okay? But we also have to square the multipliers as we are squaring those original standard deviations. Everything over here is getting squared. So it's 500 squared times deviation of x squared. 300 gets squared times deviation from y squared. And then I add those together and take a square root at the end. All right, moving right along to part E. Let's make a variable to represent the difference in number of A's earned by Preston and Oliver. The problem doesn't specify, but order is important for subtraction. So let's decide that the intent here was Preston minus Oliver, in which case my variable D for difference would be X minus Y. And as always, the updated mean will be very intuitive. I can simply take the original X mean minus the Y mean. All right, so on average, the difference in the number of A's between these two characters each semester is 0.4. Now, standard deviation, again, is a bit more complicated, perhaps not what you would expect intuitively. What I want you to notice right away, even though I am subtracting two variables, I still see addition in this formula for standard deviation. We're not going to get into the complicated mathematical proof of this right now, but suffice it to say that when there are two variables involved, whether we're adding them or subtracting them, we expect the amount of variation to increase as opposed to decrease. All right, so for that reason, sort of informally, we explain why there is a plus sign here. It will always be a plus sign in this formula for combining to find a standard deviation. All right, so the phenomenon that occurs off of that is we get the same exact result as what we got back in part C. Whether it's x plus y or x minus y, the standard deviation is the same. All right, one more part. Part F is somewhat similar to part D, but again, now we're looking at a difference in money paid. Okay, so if we call this difference W, we would say it's equal to 500 times X minus 300 times Y, which again, the mean is straightforward. I can take 500 times the original X mean minus 300 times original Y mean and get a monetary difference, a mean difference. But the standard deviation has all the tricks and bells and whistles that we've seen throughout this page. I need to square the original deviations, including these multipliers on the variables. 500 squared, deviation of x squared, 300 squared, deviation of y squared. I need to add the two products together. We're always going to add, and then finally at the end, take the square root. And remarkably, but perhaps not surprisingly, we get the same standard deviation for F as what we got for part D, because those two variables were similar with just a plus and a minus as a swap out there. Okay. If you have questions on this, you can stop by after school today. I'll be around in room 255, or you can email me, or we can talk about it in class tomorrow. Thank you.